Somewhere in the universe, something just happened. In less time than it takes you to blink, a single millisecond, a blast of radio energy erupted from deep space. It released more energy than our sun will produce in 3 entire days. Then it was gone. No warning, no explanation, no trace. Scientists call them fast radio bursts. And they are, right now, one of the most intensely studied and least understood phenomena in all of astronomy. We have detected thousands of them. We've pinpointed where some come from. We've watched some of them repeat. And we still, after nearly 2 decades of research, do not fully understand what creates them. Welcome to Space Secret Explained. Today, we're going deep into one of the strangest mysteries in modern astrophysics. Signals that arrive from across the universe in the blink of an eye, carrying secrets we are only beginning to decode. What is a fast radio burst? Before we talk about what fast radio bursts are, let's clarify what radio waves actually are, because this surprises a lot of people. Radio waves are light, not the visible kind, but electromagnetic radiation at much longer wavelengths. They travel at the speed of light. They pass through walls, gas clouds, entire galaxies. The universe produces them constantly from pulsars, supernovae, black holes, active galactic nuclei. A fast radio burst, an FRB, is a burst of radio waves that arrives at our telescopes extremely briefly, typically just a fraction of a millisecond to a few milliseconds. That's it, a flash, then nothing. But here is what makes them extraordinary. Despite how brief they are, they carry an enormous amount of energy. A single fast radio burst can outshine an entire galaxy for that 1 millisecond, and they arrive from enormous distances, not from within our galaxy, from other galaxies entirely, from billions of light years away, which means whatever is creating them must be almost unimaginably powerful. How we detect them? We detect FRBs using large radio telescope arrays. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, in British Columbia has become the world's most prolific FRB hunter, detecting hundreds of new bursts every year. Its unique half-pipe cylinder design allows it to survey enormous sections of sky simultaneously rather than pointing at single targets. But detecting the burst is only the beginning. The real detective work starts after the signal arrives. The discovery. The first fast radio burst was discovered entirely by accident, and it wasn't discovered when it happened. It was found 4 years later, buried in archived data. In 2007, astronomer Duncan Lorimer and his student David Narkovic were going through old survey data from the Parkes telescope in Australia, searching for pulsars, the spinning neutron stars that emit regular radio pulses. Buried in data from 2001, they found something that fit no known category. A single, enormously bright radio pulse, lasting about 5 milliseconds, that had arrived from somewhere far outside our galaxy. The signal had a telltale fingerprint called a dispersion measure. Radio waves at different frequencies travel at slightly different speeds through intergalactic material. Lower frequencies arrive a little later than higher ones. The amount of this delay tells astronomers how much matter the signal has passed through, and therefore roughly how far it has traveled. This signal's dispersion measure was far too large to have come from within the Milky Way. It had traveled billions of light years. It was definitively extragalactic, from another galaxy entirely. It became known as the Lorimer burst. For years, astronomers debated whether it was real. Instrument glitches, satellite interference, and, in one of the best stories in modern astronomy, staff microwave ovens were all investigated as possible false signal sources. But more bursts were found, in archived data, than in real time. By the mid-2010s, it was certain. Fast radio bursts were real, extragalactic, and completely unexplained. How powerful are they really? Let's try to really understand the scale. because the raw numbers for fast radio bursts are almost impossible to absorb. Our sun outputs about 3.8 times 10 to the power of 26 watts continuously for 4.6 billion years. Every second, an almost incomprehensible flood of energy. A single fast radio burst, in its millisecond of existence, releases roughly the same energy as the sun produces in 3 whole days. Not 3 seconds. 3 days, compressed into 1,000th of a second. To frame it differently, the most powerful nuclear weapon ever detonated was the Soviet Tsar Bomba, about 200 petajoules. A fast radio burst releases somewhere between 10 to the power of 34 and 10 to the power of 38 joules. That is between 1 billion and 100 billion times more energy. In a millisecond, whatever produces a fast radio burst is not a slow, sustained process. It is a catastrophic, instantaneous release, a cosmic gunshot. And understanding what pulls the trigger is one of the biggest open questions in modern astrophysics. The leading theories. So what is actually creating fast radio bursts? Here are the leading scientific theories, and the debate is still very much alive. Theory 1. Magnetars, the frontrunner. The current leading explanation is magnetars, a rare type of neutron star with magnetic fields so powerful they are essentially incomprehensible. A magnetar's magnetic field is roughly a quadrillion times stronger than Earth's. They are the most magnetically extreme objects known to exist. In April 2020, the case became very strong. Astronomers detected a fast radio burst from inside our own galaxy for the first time ever. It came from a known magnetar designated SGR 1935 plus 2154. For the first time, we caught a magnetar producing an FRB-like burst. Direct evidence. A watershed moment. The proposed mechanism. Starquakes. The neutron star's crust, under the unimaginable stress of its magnetic field, cracks. When it ruptures, magnetic energy is released catastrophically as a burst of radio waves. For repeaters, the crust cracks repeatedly, or the magnetic field continuously drives new stress fractures. Theory 2. Merging neutron stars. Before the repeating FRB discovery, merging neutron stars were a prime candidate. 2 neutron stars spiraling into each other release enormous energy in a single catastrophic event, consistent with a non-repeating burst. This still plausibly explains some apparently one-off FRBs. We've directly detected gravitational waves from neutron star mergers. Whether they also produce FRBs remains an open question that multi-messenger astronomy may soon answer. Recent discoveries. The pace of discovery in fast radio burst research is extraordinary. For the first decade, scientists worked with a handful of events. Today we have catalogued over 1,000, and the number grows every week. CHIME detects a new FRB roughly every day. Its design, 4 enormous cylindrical reflectors that survey huge swaths of sky simultaneously, catches bursts that any pointed telescope would simply miss. In 2022, a burst designated FRB 20220912A attracted widespread attention. It produced hundreds of sub-bursts over just a few hours, a rapid-fire cluster of signals whose internal structure was extraordinarily complex. Individual pulses drifted in frequency in ways that don't fit neatly into any single model. It remains one of the most carefully studied FRBs ever detected. And in 2023, astronomers accomplished something remarkable. They used FRBs as a precision cosmological instrument for the first time. By measuring the dispersion measure of a burst that had crossed billions of light years, they directly measured the density of gas in the cosmic web, the enormous filamentary structure of matter connecting galaxy clusters across the universe. Fast radio bursts are becoming not just a mystery to solve, but a tool to solve other mysteries. What comes next? The next few years in fast radio burst research will be transformative. Several major developments are converging. The The Square Kilometre Array, the SKA, is currently under construction across South Africa and Australia. When fully online, it will be the world's largest radio telescope by an enormous margin. Its FRB detection rate will dwarf anything we've seen, and it will localize bursts to individual host galaxies with extraordinary precision. Multi-messenger astronomy, simultaneous detection of the same event in radio, gravitational waves, and gamma rays, will finally allow scientists to pin down the physical mechanism. Catching a single FRB across multiple telescopes and detectors at the same moment could resolve the debate over origins overnight, and FRBs themselves will become one of the most powerful precision tools in cosmology, letting us map the cosmic web, independently measure the expansion rate of the universe, and probe intergalactic space in ways nothing else can. The signal arrived in a millisecond. Decoding its full meaning may take a generation, but we are getting closer every single day. Somewhere across the universe, right now, something just fired. A millisecond of unimaginable power, crossing billions of light years, carrying the fingerprint of a source we may never fully identify. But every burst we catch teaches us something about the engines that power the cosmos, about the matter between the galaxies, about the limits of the physics we think we know. Fast radio bursts arrived as a mystery. They're becoming a key. The universe is trying to tell us something, and we are, very slowly, learning to listen. If this opened up a corner of the universe you hadn't thought about before, subscribe to Space Secret Explained. Every week we take one of the greatest mysteries in space science and break it down completely. Next episode, we're asking a question that has haunted physicists for 50 years. What is most of the universe actually made of, and why can't we find it? We're going after dark matter. Don't miss it. Until then, keep looking up.